This week's lab focused on objects dropping from rest. For my experiment, I used a coffee filter and modeled the forces acting. Initially, I modeled only gravity, however, this was not a good fit. I then modeled both gravity and drag, which proved to be a better representation of my experimental results. My coffee filter was also a good representation of terminal velocity. Once again, Newton's second law helps us interpret the forces acting. Since initial velocity does not equal final, I know that the forces are in balance, and that the change is being caused in the form of speed or direction. There's also two possible forces at work: gravity, or the weight force, which is, here you can see that gravity is the mass of the filter times the gravitational constant g. And then there's drag force, or air resistance, interacting with the filter. For this model, I used the form of turbulent drag, which the drag force is directly proportional to the square of the filter's velocity times the drag constant b. I set up my initial conditions in my video, collecting data of the mass of the filter. I used a reference stick in the background of a computer. My negative y is my direction or coordinate system. I selected the point of mass throughout movement as well as my start and stop times. Here I'm showing my video multiple frames at a time for time purposes, but it was analyzed one frame rate at a time for data accuracy. I then took these initial conditions from Tracker and I set them into my VPython code, adding my mass, my initial starting position from Tracker. Here you can also see how I modeled gravity, multiplying the mass of the filter times the gravitational constant and setting up a vector in the negative y direction. I also coded my physics principles of Newton's second law, as well as my position update formula. As we watch VPython run, we will see gravity represented in the form of an arrow in the negative y direction. This arrow will be yellow. I then took these results from compared the model results to my experimental. Here you can see that the model overpredicted my experimental results greatly. The model made a change of position of almost 16 meters, while my experimental position needed only to change 1.24 meters. This means that there's another force at work. This second force, drag, must also be in the opposite direction of gravity to slow it down. So here's how I modeled my drag in my VPython code. I set my b to 0.2587, and I modeled this through trial and error to fit my experiment. I also added an arrow so you can visually see air resistance in the opposite direction of gravity. Already as we run the model, you can see that the model itself is running much slower, and this gives me hope that my data results will be much better. Comparing the two, I see already visually that this is a much better accurate fit, and it's the best fit model so far. We see that the change in distance is still negative 0.24 but for both models, and we also see that there is some discrepancy in the beginning. Now this discrepancy could be attributed to the bowl shape of the filter. As it dropped, it had lost movement in the horizontal direction as it rocked back and forth. But overall, the best fit model is gravity plus drag. In addition, we were also asked questions. What does it mean? We had to examine the velocity versus time of our models with and without drag to see which predicted terminal velocity. So what is terminal velocity? We know that air resistance acting on a falling object depends on the speed of the object. As the object drops, the speed increases, and we know that there's a non-zero net force in which air resistance is smaller than gravity. However, if terminal velocity is reached, the net force must be zero since the object is traveling at constant speed. This means that air resistance has grown in magnitude to be as large as gravity, and the forces have become balanced, equal but opposite. As we look at our models with gravity only and then gravity and drag, we can see a clear difference. Only the model with gravity and drag displays the characteristic horizontal constant velocity line that indicates terminal velocity. Our gravity-only graph tells a story of an object falling with increasing speed throughout its fall. So what if we took the coffee filter and we threw it down, giving the filter initial velocity? Will the filter still reach terminal? The chart in the top right is my object with initial velocity, and the bottom is drop from rest. Both graphs reach terminal velocity and are in fact reflections of one another. The object with initial velocity slows down as our air resistance decreases and becomes equal to the gravity, leveling out to a constant speed. while the dropped object speeds up with increasing air resistance to balance the force of gravity. Ultimately, both situations result in the same results of balanced net force of 0. This concludes my lab report. Thank you.